Welcome. Now, this is a follow-up video to the previous video in which we figured out the average rate of change, so the rate at which the water was leaking out of the tank in liters per minute on a specified interval. We discussed how that is equal to the slope of the secant line, and that was in a previous video. Now, this is the second of three videos. In this one, I'm going to show you how to estimate the instantaneous rate of change, or instantaneous rate at which the water is draining at the 3-minute mark. Now, those of you in my class, I hope in the last video you already made this change. It was more subtly presented in that video, but if you didn't do it then, do it now. And also, go ahead and change the time from the old time. You can cross it out and just write a 3. And of course, fix this typo since time in this example is measured in minutes and not seconds. So let's begin by looking at a graph of this because I think that'll really help explain how we're going to do this. So I'm using my preferred calculator, GeoGebra, on my phone, and I'm going to type in a capital V, open parentheses, T, close that parentheses, go back to numbers, equals 200 minus 4, letters here, T, and then squared, and hit enter. So now what I want to do is I want to pinch to zoom out, and I only want to pinch along the vertical axis. So if you're following along and doing this on your phone, put one finger on the positive vertical axis, one on the negative, and pinch inward. And just keep doing that till you can see a graph. There it is. I think I'm going to keep it like this. And now I'm going to do the same along the horizontal axis. I just want to see this whole thing on my phone. Now, and I'll go back to seeing the graph. I want to explore this visually around the 3-minute mark. So I'm going to open parentheses, put a 3, comma, and then a capital V, open parentheses, go back to numbers 3. This is why I really like creating the function using function notation here on GeoGebra, because it'll give me the output once I give it an input. Here on the graph, this point A represents the amount of water remaining in the tank at the 3-minute mark. So at 3 minutes, there's 164 liters of water remaining in the tank. Now, the instantaneous rate of change is equal to the slope of the tangent line. But we're not going to do it that way this time. We're just going to estimate it. And the best way to do that is to pick a point really close. So let me zoom in here. I'm squishing it down because the way I'm going to zoom in, it will help. So I want to pick some other point that's really, really close. So fairly close. So you see how I zoom my window? So down here, I'm starting at the horizontal axis from 2.6 minutes to 3.6 minutes. So I'm going to go here to Tools, go to Point, and I'm just going to tap. Oops, I already tapped by accident. I'll have to delete that one. Okay, so let me go to Algebra and delete point B. So this is at about the 3.49-minute mark. That frankly is not close enough for my taste. We could use it. So let's be more exact. I'll go ahead and type in 3 point, let's say 2, comma. And now I'm going to put a capital V, open parentheses, go back to my numbers, 3.2, enter. And those points don't look like they're that close together, but let's zoom out to our old view and you can see how close together those points are. So one thing I can do here is get a line. So I'm looking at my tools and I see line, and I'm going to tap on A and tap on B. So that line you're seeing there is a secant line. It's passing through 2 points, and look, when I zoom in, it's pretty close to the slope of the blue curve there. Look at that. Look how close they are when I zoom in a lot. Those two lines basically have the same slope. It's not exactly the same slope, but it's close enough. So I'm going to find the slope of this line, and that's going to help me estimate the instantaneous rate of change because it's really, really close to what the tangent line at A will look like. And we'll explore that in the next video, in the third of these 3 videos for this example. So Let me go ahead and zoom out. Now, the idea is when you're estimating an instantaneous rate of change, it's a better estimate if I use this line up close. So let me go back here. Oh, and actually, I'm going to delete this line. I can't delete this line yet. Oh, I just let the cat out of the bag, but I'll talk about that in a little bit. Let's do one more point. Let's go say 5, comma, v of 5. There we are. And now, let me hide my graph, or excuse me, my algebra again. And let's go back to tools. And let's get a line again. So here's line. And I'm going to tap from A to C. Now, let's take a look at these. Which one of these matches the slope of our model better? And to help us discuss the differences, I'm going to make this line by going into settings a different color. I'm going to set it to this orangish color, orange yellow color, and the original line, I'll go to my settings and I'll make it pink. I like pink. That's a good pink, nice dim pink. Okay, so our original model is this blue line. And if I zoom in really close, which line, the yellow line or the pink line, matches the blue line better? Well, the blue one, of course. So this is why when you're estimating an instantaneous rate of change, let me zoom out again, you want to choose a point that's really close. So really close. Point B is a lot closer to A than point C. And frankly, I could have chosen a point even closer, but I think that's close enough for this purpose. And, on assignments in my course, you can choose a different point if you would like. But for me, I'm going to choose this point B. So now let's go ahead and work this out. What I mean is V instantaneous is approximately equal to V average, and I should be more specific, V instantaneous at t equals 3 is approximately equal to the average rate of change from 3 to 3.2 minutes. And this is equal to V of 3.2 minus V of 3 divided by 3.2 minus 3. So this here is how we will get the slope of that line from our graph. Okay, so let's work this out. What is V of 3.2? So when I put in 3.2 into this function, like this, 200 minus 4 times 3.2 squared, there we are, minus this one here. So let's be clear. This is us evaluating this function at 3.2. And now I'm going to subtract this same function here, evaluated at 3. So 200 minus 4 times 3 squared. And just for ease, let's also color code that. And on my denominator, I have 0.2. Is that difference? So now I can go back to that question I asked earlier. What does this work out? V evaluated at 3.2. Take a moment and pop this into your calculator. Okay, you should have put this into a calculator to get 159.04. And then from that, we're going to subtract this value here, 200 minus 4 times 3 squared. So that's V evaluated at 3. Please go ahead and input this into your calculator as well. You should have gotten 164, and this whole quantity will be divided by 0.2. All right, in your numerator, you get negative 4.96. In our denominator, we still have 0.2, so let's go ahead and take care of this. And we get negative 24.8. Now, remember when I said I let the cat out of the bag a little bit earlier? Well, that's because if we take a look at our graph, when I went to the algebra view, look at our pink line. It is written in slope-intercept form, and that slope of that line is negative 24.8, which is exactly what we got. So clearly, I'm certain you all can infer that you can use tools like these to check your answers to make sure you're correct. However, those of you in my course still need to show all this work to avoid getting insufficient justification written on a problem, which means you get 0 points for it. So definitely show your work, but check it using the techniques I just showed you on the calculator. All right, let's go ahead and explain our answer. At t equals 3 minutes, the water, is draining from this tank at a rate of about 24.8 liters per minute. And again, those of you who are looking at this and going, she forgot the negative, remember that this part here, the draining, this represents the negative in negative 24.8. Water draining out of something clearly implies a negative rate of change. Water going into something represents a positive rate of change. All right, please keep calm and math on.